Hey, you guys. So we're continuing off of what we learned last time. We learned three different tests that we can run to check to see if a series will converge or diverge. Okay. So just to recap, we went over three of them. Um, Let me see if I can find it. That's strange. Okay. Tools. Okay, there we go. So we went over the divergence test, the geometric series test, and the P series test. So remember, when do we use the divergence test? Always. Okay, it's always in the back of our mind. It's a very easy way to get rid of all the bad series that diverges. So one big takeaway: make sure that you understand that if the limit doesn't come out to zero, uh, the series will diverge. Now, if it does come out to zero, it doesn't mean that it converges. It's actually just inconclusive. You don't have enough information there, okay? Now, if you happen to run into some series that have a n as a, sorry, r to the some number, right? So if n is an exponent, you definitely want to use the geometric series test, okay? And if you have n as a base, you would want to run the P series test. One big takeaway before you guys move on is that the geometric series test is the only test that actually tells you where it converges. Okay, all the other tests don't. One other big takeaway is that if you have the sum of 1 over n, just remember that it's called a harmonic series. You will see that very often, and we understand that harmonic series will always diverge, okay? So we're learning the next two, okay? We're going to come back to the integral test here. So if you go to the back of your copy here, we're going to cover the two comparison tests, direct and limit comparison tests, okay? So let me come back to that real quick. How do I go back? Okay. All right, so today we're covering the direct comparison test. Okay. And then we'll get to the limit comparison test. Okay, so first off, what I want to say is, to reiterate, these tests are very easy to apply. Okay? It takes practice remembering what the tests tell you, but the even tougher challenge is knowing which test to run. All right? Keep that in the back of your mind. So here we go. Before we do, I want to give you guys a little bit of a warm up, if you will, okay? Let's say we had 1 over x and then 1 over x plus 3, okay? In theory, and let's just assume that x is a positive number, okay? So assuming that x is positive, okay? Which of the two fractions here is larger? Okay, pause, think about it, and press play when you're ready. Okay, so 1 over x and 1 over x plus 3, which one is going to be larger, which one's going to be smaller, right? Okay, so you should have thought of this inequality here. 1 over x is going to be less than 1 over x plus 3. So to understand that logically here, okay, let's say we had x being 1. Okay, obviously 1 over 1 is 1, and 1 over 4 is 0.25. That's a quarter. So what you guys want to understand here is basically, if you add more to your denominator, you are making it smaller. I'll say that again and you should write it down. If you add more to your denominator, you will make the value smaller. Okay? Now, what would happen if you make your denominator smaller, right? What if you subtract your denominator? Okay? So here, if you subtract from your denominator, you are actually making your overall value larger. Okay? Wait a second. Whoops. That made no sense. Okay. So there you go. Take two. Okay. So when we make our denominators larger, we make the overall value smaller. So this right here is actually bigger than this one. Okay. Now if you make your denominator smaller, you make the overall value larger. Okay, just to give you an example, if x was 6, I would have 1 6 over here, and if x was 6 over here, I would get 1 over 1, which is 1. So it would lean towards that way. Okay, so to reiterate one more time, just so there's no confusion, when you add to your denominator, your value gets smaller. When you subtract your denominator, you make your value larger. Okay, very important for today's lesson. Now this one's a big giveaway. If you make your numerator larger, obviously your overall value is going to get larger too. Okay, so obviously if you make your numerator larger, you're going to make the overall value larger as well. So I'll be asking you guys these same questions throughout the whole process, but that's the very first thing that we're going to have to look for. Okay, all right. Here's a direct comparison test. Some people call it DCT. You could call it that on the AP exam. It is accepted. The direct comparison test. So basically, if you compare it to something and that something converges, then the original series will converge. Okay? Now, if you compare it to something and that something diverges, then the original series will diverge as well. Okay, so let me refer back to your tools here. Why am I not getting the notes? That's so weird. Okay, there we go. All right, so let's take a look here. The direct comparison test. Okay, so I did a little happy face here, okay? So if you compare it to something that's larger than the original series, okay? If that larger series converges, then so does the smaller series. What the heck does that mean, right? I'll explain it. Now, if you compare it to something that's smaller than the given series, and you could say that the smaller one diverges, okay, then the larger one will. So let me just give you a little picture here so that you understand what that really means. Okay, so remember that when we're finding the area under the curve, right? We're finding if the amount of space, the amount of area is finite or infinite. So just think of it this way. Let's say that let's say that, how come that doesn't work? That's strange. Okay, let's say that this is your original series. All right, let's say that this is your original series, and let's say that we compared it to a series that's definitely larger than the original series. Okay, if we can prove that the larger series converges, okay, meaning there's a finite amount of space, okay, if we can say that the larger series converges, we can then conclude then, you know, if the larger series is finite, if it converges, then the smaller one definitely has to converge too. Replay that a couple times. Okay? If we can show that a larger series converges, then the smaller series has to converge as well. Okay? Or let me give you another scenario here. If, let's say this was your original series. Okay? Now, if we came up with a series that's definitely smaller, okay? But I can show you, we can somehow prove that this smaller series diverges, okay? Now remember, diverges means that the area goes infinite. If I know that the smaller series diverges to infinity, I could then say that the original series must diverge as well, because if something that is smaller than it, right? If something that is smaller than it goes to infinity, then definitely something that's larger than it has to go to infinity as well. Okay? Let's put it to the test here, okay? It's okay if you got to replay this a couple times, but it might make more sense once we do an actual problem. So here we go. Here's example 1. Write it down. Part A. Okay, so what we want to do here is, obviously, we're going to run through the divergence test. I quickly see that when n goes to infinity, I'm going to get 0 here, so the divergence test doesn't tell me anything. This doesn't look like a geometric series because there's no n exponents. And this kind of looks like P series, but not really because of this plus 3 here. Now, if the plus 3 wasn't there, then that would definitely look like a P series, okay? So here's what you do. You want to compare it to something that you do recognize. So I'm going to go ahead and compare this here. And what you're going to compare this to is you're going to pretty much give me the most basic form of what you see right here. So what I like to do is I like to get rid of all the constants. Like this plus 3 right here. I want to just imagine as if it was gone. So the most simplest thing that I can think of is 1 over n squared. This takes a little bit of practice, and you guys will see. All right? So let's do that. You know what? Let's do that over here as well. Okay? So here, just to get you guys used to comparing it, the most basic form here would definitely be 1 over 3 to the n, because I'm just ignoring that constant 2. All right? Over here, I would definitely compare that to 1 over n squared if I just get rid of the constant there, just so you have an idea. And over here, most people would put 1 over 2n because they got rid of the 1. But even this coefficient right here doesn't even matter. So the most basic thing about this problem is that it looks very similar. I'm going to compare it to 1 over n. That 2 really doesn't matter, and I'll show you in a second, okay? Let's do a couple more so you get the hang of it. Over here, think about what you would compare that to and then press play, okay? This would be 1 over the square root of n, or 1 over n to the 1/2 power, because you just ignore the 2. Try this one here. This one here, if I got rid of the 7, I would get n over the square root of n to the 4th. All right? But even then, this can be simplified. That's the same thing as n over n squared. And even that can be simplified into 1 over n if you reduce. Okay? So I could actually compare it to 1 over n. All right? Over here, if I got rid of the constant, I'm just going to be left with n over n cubed to the 3/7. But again, I can clean that up. That's the same thing as n over n to the 9 over 7ths. And even then you could reduce that. That's the same thing as you subtracting exponents. So that's just going to be 1 over n to the 2 sevenths. Alright, because 1 minus 9 sevenths will give you negative 2 sevenths, which gives you this. I know I'm moving a little bit quickly, so please replay if you need to. Alright? Okay. One more just to make sure you guys get the hang of it. Okay. This one here. This is a special case, but it's fair game on the AP exam, okay? Sine, if you understand how sine works, the graph of sine, the furthest it's going to go is a plus or a minus 1. Alright? So, we can simplify that down to 1 over n to the 3 halves. Because although sine is a function, it doesn't really get that large besides 1 or negative 1. So we could compare it to that. Alright? More on the comparison in a second, but let's actually show you how to do a problem here, okay? So going back to part A. You will have time to copy all the other ones down. So I know I rushed it, but just wait until we get to that example, okay? Here's what you want to know. Okay. Can you guys tell me which series is larger or smaller? Alright? Notice how this one has a plus 3 in the denominator. So think back to the very beginning of today's notes. What happens when I make my denominator larger? What happens to the overall value? Pause and press play when you're ready, okay? Okay, so when we make our denominators larger, the overall value gets smaller. So I am able to state that this series here is less than what I'm comparing it to. Okay? Text me if you have questions. Okay, it's something that you guys got to get used to, so I understand it if it's not so transparent. So here's what we do. We're going to take a look at what we compared it to, okay? Now, obviously, I would want to bring over n equals 1 to infinity here. Now, this series over here, all right? 1 over n squared. What test would you guys run to show that this converges or diverges, okay? What does this closely resemble in terms of which test you should use? Press play when you're ready. Okay, since I noticed that it's 1 over n to the something power, this looks just like P series, okay? And here, P equals 2. So let's look back at our notes here. Look at your worksheet for P series. For P series, when P is 2, which is larger than 1, I know that it will converge. All right? So, therefore, this right here converges. How do I know that? By P series. So here's the thing. I didn't ask you guys if this series converges or diverges. I'm worried about the original one. So it goes back to this concept that I drew up here, okay? According to my inequality right now, this is the larger series. And I just proved to you guys that the larger series converges. So look, if the larger series converges, then that means the smaller one has to converge as well. Let me use different words here. If the larger series comes out to a finite area, meaning there's a number, a specific amount of space, then the smaller one has to be a specific amount of space as well. So, play that a few times, all right? Therefore, the summation of 1 over n squared plus 3, as n starts at 1 to infinity, will converge as well by the direct comparison test. Okay? Be very logical about this, you guys. If the larger series that we compared it to converges, then anything that's smaller than it has to converge as well. All right, let's try a couple more. Here we go. So we compared it. We compared this to 1 over 3 to the n. I'll bring over the starting value and the ending value. What test would you guys run here? Okay. All right. Now, obviously, divergence tests we're always going to run, but often cases it's not going to give you enough information here, okay? I noticed that n is an exponent, which is a clear sign that we should definitely use the geometric series test. Now, this should definitely be rewritten as 1/3 to the n power. Okay? We talked about that in the last lesson. Okay, so here, r is 1/3, which is definitely less than 1. So go back to your tests here. You guys have it in front of you. For a geometric series test, if r is less than 1, we know it will converge. Okay, says so right there. All right, so here we go. Therefore, converges by geoseries. Okay, but I don't care about what I'm comparing it to. I want to know what happens with this one. Okay, so we go back to this situation again. Can you guys put a less than or a greater than sign here? Okay, what would it be? Would it be less than or would it be greater than? What would it be? Press play when you're ready. If I'm adding 2 to my denominator, I'm making the overall value smaller. So this has to be less than what I'm comparing it to, okay? I just proved to you guys that the larger one converges. So does that tell me that the smaller one will converge as well? It sure does. Therefore, the summation of 1 over 2 plus 3 to the n, as n starts at 1 all the way to infinity, will converge as well by the direct comparison test. It's a little bit of writing. If you notice, there's not a lot of work. It's just a lot of thought process. Okay? All right, let's keep going. Here's part C. So we compared it to 1 over n squared because we got rid of our constant. So this looks like a pretty much basic 1 over n squared, but there's a minus 1 to it, right? Okay. Less than or greater than. Press play when you're ready, okay? Okay. We made the denominator smaller, which means that the overall value gets larger. So this is greater than here, okay? All right, so let's keep going. Here we have n equals 2 all the way to infinity. Let's take a look at what we're comparing it to. What test would you guys run there? Press play when you're ready. This is definitely P series. I know that P is 2, which is definitely greater than 1. And when P is greater than 1, let's go take a look. And you guys want to look back, but don't rely on it, okay? Because assuming that we take this test in person, they won't give all this information to us, okay? So since P is greater than 1, we know it will converge. Therefore, 1 over n squared will converge, or converges, whatever you guys want to write. How do we know that? By P series test. There you go, there's Siri again. Okay, but I want to know about this one. Okay, so let me label this for you guys real quick. According to this inequality, this is the larger series on the left here, the original one. I showed you that the smaller one converges. The smaller series converges. Does that guarantee that the larger one will converge too? So let me give you a different scenario here. if the smaller one converges to the number 8, finite, right? Does that guarantee that the larger one will converge to a finite value as well? It actually doesn't. It doesn't guarantee, because that larger series could easily diverge. Okay? So here, notice how the direct comparison test did not work. All right? I wasn't able to guarantee it. So we don't conclude that it diverges or converges here, okay? This, for now, until the end of this lesson, we don't know enough. So we're just going to say, for now, inconclusive. You'll learn throughout this whole unit that you need to use the right test to get the right answer, okay? This direct comparison test I'm showing you guys right now, we were able to compare it, but we were not able to conclude that it converges or diverges here. Okay? So for now, we don't know enough, so we're just going to say it's inconclusive. All right? So we'll come back to that one. Here's another one. Here's part D. Okay? We were able to explain earlier that this series, if you were to simplify it to its bare bones, it looks like 1 over some type of n. Okay? Again, that 2 really doesn't matter. All right? Okay. This is where it gets a little weird. All right? We're adding 1 to the denominator, and we're also multiplying it by 2. So this one is obvious that the denominator is getting larger, which means that the overall value is getting smaller. Sometimes it's not so obvious on what's larger or smaller. Keep that in mind, all right? So let's pursue this here. Here, what do we know about this series? Well, you guys could definitely run P series because it's 1 over n to the something. You find out that P equals 1. And then if you look at your chart, you find out that it will diverge. Or you recognize that 1 over n is just a harmonic series. So here we could state that 1 over n will diverge since it's harmonic. Or you could say because of P series. Up to you. But again, I tell you, this pops up a lot, so remember harmonic series, okay? All right, so we, let me label it for you guys. We established that the one that we're comparing to is larger based on our inequality here, and this is the smaller one, right? Okay, we just showed that the larger one diverges, meaning it goes on to infinity. So does that guarantee that the smaller one will diverge too? Think about that there. And press play when you're ready. Okay? If the larger one diverges, does the smaller one diverge as well? Okay? So let's go back to this picture. Here, we have to prove if the smaller one diverges, then the larger one will, right? So, just because the larger one diverges doesn't mean that the smaller one can't converge. So, we're stuck at a pickle again, just like in part C. We don't have enough information. So here, for now, it's inconclusive. Okay, until you reach the end of this lesson, okay? So you've seen 2 examples where you could actually use direct comparison tests, and here you see 2 examples where it didn't really work out in our favor. Okay? Okay. So let's try a couple more. Here's part E. Okay? Write it down. Press play when you're ready. We were able to compare that this is very similar to 1 over n to the 1/2, or 1 over the square root of n. is this less than or greater than? Press play when you're ready. There's a 2 plus there, so we're making the denominator larger, so the overall value is getting smaller. So this is a less than, all right? Okay, here, based on P's series, since P is 1/2, which is definitely less than 1, if you take a look at that chart, okay? When P is less than 1, we know it diverges, okay? So therefore, this here diverges by P series. Okay, so we just showed that the larger one diverges. So does that mean the smaller one will diverge too? It doesn't, right? The smaller one could easily converge. All right, so again, inconclusive. You guys are probably tired of all these inconclusive ones. Don't worry, we will eventually figure out how to do those. Here's part F. So remember here, most people would write n over the square root of n to the 4th, but down to its bare bones, if you were to simplify it, it would just be 1 over n, okay? Okay. If I add 7 to the denominator, okay, I make my denominator larger, but I make the overall value smaller. Okay? Same situation, okay? I know that this is harmonic. So, definitely diverges. The larger one here diverged. So does that guarantee that the smaller one will? Okay? And here's another thing. I'm not so sure about that inequality because there's another n up here as well. So as n is getting larger, so is the top. So like it's, if you notice, if you have to think twice about it, if you're thinking longer than 5 seconds, if it's larger or smaller, most likely direct comparison test is probably not the way to go. And I'll emphasize that, okay? So here, again, inconclusive. All right, let's do another one. Again here, I know that the -1, right, makes the denominator smaller, but I also noticed that n is also changing up here. So it's really tough to tell which one's larger or smaller here. So I'm going to say that this is also inconclusive. When you can't make a quick comparison, so within 5 seconds, if you can't tell me if this is less than or greater than, most likely that tells you that direct comparison test is not the way to go. Okay? Same thing here. Here, you could kind of make a comparison, but it takes a little bit of thought. Knowing that sine is at most 1 or -1, this is definitely something less than, at most equal to. But I'm not going to put the or equal to, okay? So at most, we know that this has to be less than the other one, okay? So again, sine will come out at most plus or minus 1 at the top. So in the chance that it's anything less than 1, right, it has to be a less than inequality here. So again, that's not super transparent, but this is also a very rare case. So we can't say that this is less than. According to P series here, tell me what happens and press play when you're ready. Since P is 3/2, we know that's greater than 1. And when P is greater than 1, we know it's going to converge. Converges by P series. Okay, so according to my inequality, this is the larger one. The larger one converged. The larger one converged. So does that mean that the smaller one will converge too? Absolutely. When a larger series converges, if the larger series is finite, then anything smaller than it has to be finite as well. So therefore, sine squared n over n to 3/2 converges as well by direct comparison test. All right? Things will make a lot more sense when you guys learn your final test here, the limit comparison test, all right? Okay, I'll start off with the when, okay? When should you use the limit comparison test, or LCT here? So I mentioned it before. If within 5 seconds you cannot tell which one is larger or smaller, then you should most likely use the limit comparison test. Okay? Same thing with the limit comparison test. It doesn't always work. So you're not always going to use the limit comparison test, okay? Using the actual test is easy. Knowing which test to use, that is the big challenge for this unit, you guys. So practice that, okay? All right. So the limit comparison test is basically this. You take the general term off of your given series and you compare it and you put it underneath the compared general term and you take the limit as n goes to infinity. Based on what happens here, that'll tell you a few things. So here, it's a little bit tough to read, but I break it down in your worksheet here. So take a look. The limit comparison test. One thing is going to happen. If you take the limit and the limit comes out positive and finite, okay, so not infinity. So if it comes out positive, that tells you that both series behave the same. And that's it. Okay? More on that later. Now, if it does come out to 0 or infinity, then it's inconclusive. You got to use a different test. All right? So notice how here with the direct comparison test, I told you guys, with a quick glance, if you can't distinguish which one is less than or greater than, then the limit comparison is probably the better option. All right? Okay, so this A sub n and this B sub n, I also made a note that it doesn't matter which one goes on top or which one goes on the bottom. And it'll make more sense once I show you what I mean here. Here we go. Here's example 2. Last example with parts A through Z. Here we go. Part A. Divergence test tells me that this is going to go to 0, so inconclusive. This definitely doesn't look like a geometric or a P-series test. What I'm going to do here is I'm going to compare it. So down below, this mentally will break out to n squared plus 2n plus 1. If you're looking at the bare bones of it, you're looking at pretty much the largest degrees. So really what I'm doing in my head is I'm only looking at 3n and n squared. Because when n gets really large here, that 2, that 2n, and that plus 1 will not matter. Okay? So the bare bones of it is 3n over n squared. But I noticed that I could actually simplify that as well. So remember, coefficients still don't even matter. So I can actually get rid of that 3. That 3 actually goes out here, but it doesn't matter in terms of convergence or divergence. So I'm going to erase that. N over n squared will reduce out to 1 over n. Again, finding out what it compares to takes a little bit of practice. But if you notice here, I ignored all of my constants and coefficients. I'm just looking at the largest degree term in terms of the variable. All right? Okay. So here's what I mean, you guys. Normally, I would try to use the direct comparison test. Both the numerator and the denominator are being affected here. So for instance, the numerator is getting larger, but so is the denominator. So I can't quickly tell what the overall value is going to come out to, right? I can't quickly say if it's a less than or a greater than. So I am going to try to use the limit comparison test, all right? So here we go. What you're going to do is you're going to take the limit as n goes to infinity, And it doesn't matter which one you put on top or which one you put at the bottom here. But I'm going to go ahead and put my original one at the top. And what I'm comparing it to at the bottom. All right? Okay, so here we go. How do I divide fractions? Okay, I'm going to go ahead and multiply by the reciprocal here. So the limit as n goes to infinity will be the same thing as 3n plus 2 all over n plus 1 quantity squared times n over 1. All right? So if you multiply this out, and again, n is going to infinity here. So all I'm concerned with is the largest degree term. So I'll write it out this time, but really you guys will save a lot of time just by analyzing what you have in front of you. So for instance, if I distribute this n here, I get 3n squared plus 2n. But knowing that, I don't need to know any of the terms that are smaller than the highest degree. Right? But I'm just going to write it out this time. Down below, I'm going to get n squared plus 2n plus 1 if I multiply it out. Okay? But really what I'm doing, you guys, here's what I'm doing in my head. And you guys will too. When I multiply this out, I'm thinking, okay, you know what? My largest degree term has a 3n squared at the top. The bottom one, the largest degree term, is just going to have an n squared. That's really what you guys are doing. Okay? So, here we go. N is going to infinity. So this goes back to that conversation regarding speed. Where is it getting larger faster, right? They are both getting larger faster equally because they're traveling at the same speed. So you look at the coefficients. This right here will come out to 3. All right, what the heck does that mean, right? So remember, if we go back to this test, the limit comparison test states that as long as it comes out positive, okay, and finite, both series will behave the same. So look, check it out. 3, definitely positive. Therefore, both series behave the same. Okay? So if one series converges, the other one will converge as well. If one series diverges, the other one will diverge as well. This is not a conclusion yet. We've just proven that these two series that we wrote down will behave the same. But here's the thing. I know exactly what happens to this series. Okay? So what we can say is, since this series diverges, and how do we know it diverges, you guys? P series or harmonic. Therefore, 3n plus 2 all over n plus 1 quantity squared will diverge as well. How do we know that? By the limit comparison test. All right? A lot of thought process, but it's not that bad. It's very conceptual. All right? So let's go back real quick to one of our inconclusive ones. Check this one out here. This is example 1 part C. We the smaller series converged, but that didn't guarantee that the larger one will, right? So take a look here. What if we were to run the limit comparison test? So the limit as n goes to infinity, and again, it doesn't matter which one goes on top, but I'll just go in order. Okay? If I clean this up here, and you don't have to write this down, just understand it. The limit as n goes to infinity, I notice that my writing gets worse and worse as the lesson goes on. I get something like this. And if I'm staring at this correctly, both top and bottom are traveling at the same speed. So I look at the coefficients and it will come out to 1, which means that it's positive. So I know by the limit comparison test, they both will behave the same. So see, now that I know they behave the same, back when we were focusing on this, I know that that converges by p-series. So according to the limit comparison test, this series is going to have to behave the same, meaning it has to converge as well. Okay? I'm not going to do all the inconclusive ones, but you guys can definitely go back and check, okay? So here we go. Here's part B. Okay? Think about what you're going to compare it to and then press play. I would definitely compare this to 1 over 2 to the n. Or in this case, I could rewrite it now so I don't have to do it later as 1/2 to the n power. Make sure that you guys understand why it's equivalent. Okay? Now, here I am able to compare it. I am able to say that since I'm making the denominator smaller, the overall value is getting larger. Okay? But when I tried to use the direct comparison test, I found out that my smaller series diverges based on the geometric series. So that doesn't guarantee me that the larger one will diverge. So this is where the direct comparison test failed. Okay, I know I said that pretty quickly, so replay that. Okay, so look, what I'm going to do is I'm going to run the limit comparison test. So I'm going to take the limit as n goes to infinity. It doesn't matter which one goes on top or on the bottom. And I'll go ahead, I'll go ahead and write it like this for the sake of limits, okay? So if I take the limit here, I'm going to have the limit as n goes to infinity of 1 over 2 to the n minus 1 times 2 to the n over 1. So when n goes to infinity, I notice that both the top and the bottom travels at the same speed of 2 to the nth power. So this comes out to 1, which is positive. Pause and play here, okay? Think about the implications when it comes out positive. That tells me that both series will behave the same. Not quite the conclusion just yet, but we know that by the limit comparison test, both series will behave the same. So we have to dig a little bit deeper here. What do you guys know about this one? Okay. Run your tests. Give me your conclusion. Press play when you're ready. So this is definitely geometric series test. Since r is less than 1, I know this is going to converge by geo series. Okay, and I can show where this converges to, but remember, your main focus is showing what that converges to, or if that converges at all, right? So since that one converges, I know by the limit comparison test that the original series will converge too. Therefore, 1 over 2 to the n minus 1, I'm running out of space here, will converge as well by limit comparison test. All right. Definitely text me. Definitely remind if it's not sticking, okay? Let's do a couple more. Part C. Try that out on your own. Go as far as you can if you like. And then press play when you're ready. Okay, this right here, down to the bare bones, if you did it right, if you got rid of the lower degree terms, you should get that. If you get rid of the 2, you would get n over n cubed, and if you reduce it, you would be down to 1 over n squared. Okay? There's a lot going on in the numerator and the denominator here, so I don't know if this is going to come out less than or greater than. Okay? So that tells me I should probably use the limit comparison test. So here we go. The limit as n goes to infinity of whatever over the other one. Again, it doesn't matter which one's on top, which one's on the bottom. Okay. Multiply by the reciprocal. Okay, if I study this without having to multiply it out, the largest thing that I'm going to get on top is a 2n cubed. And the largest term I'm going to get at the bottom is an n cubed. I notice they're traveling at the same speed, so I look at their coefficients. So the coefficients are going to come out to 2. But more importantly, it's positive, which implies that both series will behave the same. Okay? But still, that doesn't give me any information on what happens to the original series here. So I take a look at what I compared it to. That is definitely P series, P equals 2, which is definitely greater than 1. Okay? So you go back to your chart one more time. And again, don't rely on it too much. P series, when it's greater than 1, we know it converges. Okay? Therefore, converges by P series. Okay, well, I stated earlier that these two series will behave the same, and I just proved that one of them converges. Therefore, two n plus 1 over n cubed minus 2n will converge as well. How do we know that? By limit comparison test. You do enough and it'll stick, you guys, okay? It's obviously new, and with anything new, it's always going to be a little bit uncomfortable until you start practicing, okay? Okay, here's one more. And I have a couple more. Here's one more, part D. Try that out. Press play when you're ready. Okay, here I would definitely compare this to 1 over n squared. That 3 really doesn't matter, as well as the negative 4n plus 5. Okay, I can't say if this is going to be larger or smaller. The plus 5 will make the denominator larger, but we can't say what's going to happen with the negative 4 and the 3, right? It's tough to tell. So we'll leave it empty. We're going to say the limit of 1 over 3n squared minus 4n plus 5 as n goes to infinity. Let's do all over 1 over n squared. If you guys crank that out properly, you should get 1/3. But more importantly, it's positive. You're just looking for a positive answer, okay? Now, if you flipped it, if you wrote 1 over n squared at the top and then 1 over 3n squared at the bottom, you would get a different answer for your limit. You would get 3, but notice how that's still positive, okay? Therefore, we know it behaves the same. Behaves the same. Okay? We know this right here from our last example that it will converge as well by P series. Okay, I'm running out of space, but you guys should definitely write it out a lot neater than I am. Therefore, 1 over 3n squared minus 4n plus 5. I keep forgetting my index, but let's write it. Will converge as well by LCT, the limit comparison test. All right. Well, I have a lot for you guys. Okay. Let's do this last one here, and then we'll call it a day. Okay? Try it on your own. We'll call this part Z. And then press play when you're ready. Okay, I would definitely compare this to 1 over n cubed. If you didn't get that, ask me or ask your peers, okay? All right, I can't tell which one's less than or greater than right off the bat, so I'm going to use limit comparison. Okay. I'll have n squared minus 10 all over 4n to the 5th plus n cubed. And I'm going to divide it by 1 over n cubed, or I'm just going to jump straight to the reciprocal. That way you could save a little bit of time. Okay, so in my head, I know the largest term I'm going to get at the top is n to the 5th. The largest one at the bottom, I'm going to have 4n to the 5th. This is just my stream of consciousness here. I wouldn't actually write this out, okay? So I know that that limit will come out to 1/4. But more importantly, it's positive. Therefore, behave the same. Okay, what do I know about this series right up here? Definitely P series. I know that it will definitely converge by P series. So if this one converges, then I know the other one has to behave the same. So therefore, n squared minus 10 all over 4n to the 5th plus n cubed will converge as well by the limit comparison test. Okay, that's it. I'll leave these 3 examples for you to try, but if you want to go over it, just reach out to me there, okay? So big takeaway, you guys, let's look at this test one more time. Direct comparison test, if you can easily identify if the series is less than or greater than, then you might want to use the direct comparison test. But even then, you have to understand this notion. And I recommend that you guys draw pictures, okay? If the larger one converges, then the smaller one will converge too. If the larger one converges, that doesn't mean that the smaller one will diverge, okay? So it has to make sense. Now, if the smaller one diverges, then definitely the larger one will have to diverge as well, okay? So make sure that you guys are really practicing that there. Drawing out the pictures will really help out. Now, if direct comparison test doesn't work, then that's where limit comparison comes in. Limit comparison is pretty straightforward. You're pretty much finding out the limit to come out positive, and if it is, you know that the series are going to behave the same, and then you could proceed to make a conclusion there. All right? That's pretty much it. Okay? Try it out. Practice, practice, practice. You're only going to get better at it if you do. And, you know, you're learning direct comparison and limit comparison, but that doesn't mean that these are neglected right up here, okay? You're still incorporating geoseries, P-series, and the divergence test, okay?